All right, let's hit the lights.
I can't hear you.
There we go. Wait. Okay. All right, so my summer internship was with the PennDOT Materials Testing Laboratory, which is located in Harrisburg, Pennsylvania. So a little bit about PennDOT. It builds things, so they need raw materials. So like they get the materials from like rock quarries and stuff. So they have like 800 suppliers in and out of state. Like they can get rocks and stuff from Maryland and New York. And then we have to test and qualify and requalify these products from every supplier. So we have like different types of samples, like RS is a requalification sample. That's one that comes in every 2 years. QS is a qualification sample, which is someone that's trying to get Pennsylvania to buy their materials and use on the roads and bridges and stuff. QA is quality assurance, like if they're concerned about the integrity of it. IV is investigation sample, which usually means like the sample failed and they're like curious as to why it's failing and stuff. And information is like a private research project. So it was a very dirty internship. So like that's like how I was dressed like almost every day. It was pretty casual, just like a t-shirt, jeans. Then I wore like an apron to keep all the clay and stuff off me. And then a dust mask so I don't get mesothelioma. So I worked in 2 different laboratories. The first lab was this laboratory called C2A, which is like coarse aggregate of 2A size rock. And I did like a whole bunch of different tests, like a grading and a sieve analysis. So it's this big sieve shaker that you just shake down the rocks and it separates them out from like an 1.5 inch retained on it all the way down to minus 4 squares per inch. So you just get like a size distribution for them, and you can fail that test. There's a wash test where you wash away all the fine particles. Those are minus 200 particle size, and those are the particles that hold moisture, and you don't really want stuff that holds moisture. You can send it away for a petrographic analysis. I didn't actually do petrographic specific gravity or sodium sulfate, but I prepared those samples so they could just like get them going real quick. And the sodium sulfate is kind of interesting because it's like a salt, so it's like a salt wedge that like breaks the rock apart. So like you pour the liquid crystal into the rock and then you like bake it, and like the crystal forms and like gets in the cracks of the rocks and pushes them out and breaks the rock. Then I did a freeze thaw test, a sand equivalency test, which is what you see in the pictures there, which is basically Stokes' law at its finest. You know, the heavier stuff, the bigger diameter stuff falls, and you can see like the distribution between sand and clay. You can do like a slag expansion test, like whenever like the steel furnaces and stuff, they have to use a slag to make it like pure. So then we're trying to find if there's like a use for the slag, but it's really not that great because it expands over time if it gets wet, and it's really brittle, so it breaks apart. Moisture density and LA abrasion. LA abrasion is kind of cool. It's a really loud machine. It's a really big drum. It's this picture right here. It's a really big drum and has these steel balls in it, and it like picks up the ball and it like drops it and just crushes up the rock. And almost every test is like you weigh it before and then you like do something to it, and then there's a certain criteria you're looking for, and then you weigh it again and you need like a certain percentage. And that's like how most of the tests are. And then the other lab that I worked in was the soils lab. And then you just do, similar tests, but for soils. So this picture right here is a hydrometer test. It's Stokes' law again, and you're just like trying to see how big the clay particles are. And this is a 24-hour test. So it's like demands your attention for like the first 3 hours. Like you're taking like readings like every 5 minutes on the hydrometer, and then it like starts to spread out with your times, and then you just take a reading the next day after, and then you can size the particles based on the reading on the hydrometer, because the density changes. California bearing ratio is how much pressure, I think it's, I don't know, it might be 4 tons to depress the soil 1 inch. Direct shear, I have a picture later. It's just like whenever like soil like slides on itself. Liquid and plastic limit, I forget what you're looking for with that, but like has something to do with like moisture content. Resistivity, for like whenever you're laying down ground wire, you may or may not need resistivity, so you can measure like how much resistivity the soil has whenever it gets like different levels of moisture. And then moisture density, you develop a curve like this. Yeah, so and then there's other tests that other people did, like cement really looked for entrapped and entrained air, which is like natural air occurring in, and then entrapped air is air that is included after you mix it. All right, so this is a direct shear machine. You're putting a 1 ton, 2 ton, and 4 ton pressure on these little discs of soil, and then the machine slides it, and you get like different readings for like the friction or whatever, how well it stays together and how easy it slides apart. If you're friends with me on Snapchat, you'll remember that thing. This is a compaction. That's some slag. I'm talking about the thing on the right that's moving. That's slag, and we're compacting it to try to expand it in our expansion test. And whenever the slag expands, it doesn't expand more than 40 millimeters. So it's like not like no, that's not right at all. 4/1000th of a millimeter, so of an inch, so 0.004. And then this is a liquid and plastic limit thing. It's called a Atterberg test, and you just smear the clay, and then you it's called a blow. And you do like 30 blows, and it's just dropping this plate, and you're trying to get it to close 1/2 inch right here. It's a really weird test, but it's all about like getting the right moisture content, and then you weigh it. You weigh it dry, and then you weigh it wet. Almost everything's like right before, weigh it after. It's really, really simple. But they make it sound like you're splitting atoms at this place, but it's just like adding and subtracting. There's just another view of like hydrometer. Here's what the lab looks like whenever it's all cleaned out. I don't have a picture of it whenever it's filled with, but like we have like these big 4-foot pallets that like fill up this gap right here, and they're stacked like up to here with these 90-pound bags of soil. You're just like lifting them all day. And then we had to clean it out like around 4th of July because they re-waxed the floors, so it looked pretty cool after we cleaned it out. But it's usually just lined the walls with these rock samples, and then each of these is a different lab. And I worked in this one right here. You can't see the door, but it's right there. So yeah, I hope that was fast enough. There's my Snapchat. Add me on Snapchat. And I hope you, I do recommend if you live near the Harrisburg area to apply for this internship, because there is some very shady hiring processes that goes on there. Like the guy that hired me, his brother went to St. Francis, and he hates Penn State. So he hired me just because I went to St. Francis. Not because of our name, but just like because of like, he didn't want to hire Penn State kids.
All right, thank you. Now, before Maria hits on Wait, Maria. 1, 2, 3, go.
Oh, perfect. Yeah. So I did an internship at Compliance Environmental Services and Bioremedial Technologies. It's 2 different companies owned by the same people in the same building. Compliance Environmental Services, they deal with the, like at the site characterization reports and like what's going on at the site, and the bioremediation, they do the remediation of it. Okay. So at CES, they deal a lot with underground storage tank spills, so like gas stations and stuff. So what they do first, what we do is we go to the site and we install monitoring wells and take soil samples. And then a few days later, we develop the wells. And then we have to monitor them. Every week you go and you take groundwater depth measurements. And then you take water samples, and then you do groundwater contour maps to see where the groundwater is moving, and iso concentration maps, which is like where the plume is, where like the heaviest contamination is. And then you do the aquifer testing, which you take the well that has the most contamination, you pump that, and you figure out where, like how it's affecting the water levels in the other wells to see like how the water migrates. And then bioscreens, they're analysis that deals with how the contaminant is migrating and how it will degrade over the like a certain amount of years. So after all this happens, after CES does this, bioremediation comes in and they figure out how to remediate it. So I worked a lot in the lab for this. I plated samples anaerobically and aerobically, testing for certain VOCs like benzenes and MTBE. Different procedures for plating them. We plated samples with 1 times 10 to the negative 1 dilution to 1 times 10 to the negative 4 dilution. We also did nutrient analysis on sample testing for phosphates, nitrates, and sulfates. And then they have huge things of cultures in their bay, and so I made the nutrients for those. And I did a treat study at a certain site testing for PCEs. So what a treat study is I took groundwater samples from the site, and we added 2 different remediation processes. They use like 2 different cultures, I guess, and you wait like every 14 days and you figure out like what the PCE concentration is and how that culture is degrading it. Plating. I plated thousands of samples probably. So there's different types of augers or different types of plating. There's hetero for all, and you're testing for all the bacteria there. And there's contaminant degrading auger where you're testing for the VOCs. And then for the aerobic sites, you would plate the samples and the hetero would just sit on the counter for 14 days. And the ones where you're testing for the benzene, they'd be put in a plastic tub and there'd be a beaker filled with the benzene. So those plates were only exposed to benzene for 14 days to see what bacteria grew and like what was there. And the anaerobic sites, you have to do everything anaerobically, so everything would have to be like in nitrogen bags because it couldn't be exposed to oxygen at all. So those samples we put in nitrogen bags for 14 days to see how those would grow. That's basically all I did. Sorry, that was so short.
All right, Hannah. All righty. Remember to be writing down questions if you have them.
All right, so my name's Hannah Patton. If you don't know me or recognize me, I was walking around with a new coat and a tag on it earlier today, so thanks for the heads up, everyone. That was really cool. I did summer research on campus this summer, 3rd summer in a row, because I loved it so much, and I love working with Dr. Wagner so much. And it's not sarcastic at all. I actually do quite enjoy it, so that's why I did it again. So my first summer, I guess we'll call it, my first summer doing research here was on MFCs. Who knows what an MFC is? Raise your hand. All right. So in case you haven't been enlightened yet, MFC stands for microbial fuel cells. They can look like this, or if you're a big kid, they look like that, or some variation of that. So I actually, my summer after my freshman year, Josh of English and I, shout out, we worked on microbial fuel cells with Dr. Wagner, and we played around. So what a microbial fuel cell is basically, I'll call it like a biological battery, kind of. So you inoculate it with wastewater. You have a cathode and anode like you do with the battery. There's microbes that are in that wastewater that are in this main chamber of the MFC, and they're eating up the nutrients that are in the wastewater, and there's an energy wave, and we'll just, so that they're converting those nutrients into energy, and we're harnessing a portion of that energy in the microbial fuel cell, and then that can be used to power things. As of right now, not huge things, because there's kind of a learning curve there with how much voltage that we're getting out of each MFC. So right now it's like relatively low. I think the biggest thing that Penn State right now, or at least when I went to their lab, that they were powering was like a fan with an MFC. So we're not talking about, you know, like powering a whole building right now. But that's what the research that people do on MFCs is kind of geared towards. Usually it's geared towards startup time, because there's it takes like a certain period of time for the microbes that are in the wastewater to start eating those nutrients and getting comfortable, and so there's like a kind of like a waiting period before you can like actually get good readings and good voltage, and then also like the other portion of that research is kind of trying to increase that voltage that's coming from those MFCs. So and then there's also MFCs. Also, there's like anyway. So the research that we did was mainly dealing with trying to improve startup time and voltage. So Josh and I kind of, and Dr. Wagner, kind of messed around with the anode and cathode materials to see if by changing the materials we could get a greater voltage with a shorter startup time, which is obviously preferred. So that MFC research led me reading. So obviously in research you read a lot of other people's research, because we're not experts on the, I mean, Josh and I aren't experts on the topic. So in my travels through MFC scholarly articles, I learned of the AFMBR, which stands for Anaerobic Fluidized Membrane Bioreactor. And I first, there it is, written down in case you guys were concerned. And so I first learned of this in a paper that was about MFCs being connected to anaerobic fluidized membrane bioreactors. So the water that comes from the MFC, like so obviously there's a set amount of nutrients that are in that volume of water that you put into the MFC. So over time, the bacteria and the microbes, they're eating those nutrients, and so eventually those nutrients are gone, and you have to re-inoculate and feed them over again. So that water that comes out of the MFCs turns out to be not that poor of a quality as far as like wastewater effluent goes, but it's still not water that you can like obviously not drink, but it still isn't something that you would want to discharge into a stream or anything like that. So like we even take that leftover like wastewater that's inside the MFC and we'll like bleach it and put it down to drink. It's still not clean, but it's better than it was when it came in. So what they did at Penn State, Bruce Logan, who was Dr. Wagner's graduate school advisor, has been working on kind of connecting MFCs to AFMBRs. So he's taking that water that's coming out of the MFC when they're re-inoculated, and they're pumping it through an AFMBR, and this AFMBR is in essence like polishing it so that it is of better quality and can like hopefully be discharged in environmentally, and like it can be discharged and you can feel good about discharging it, like environmentally conscious. But so I'm going to show you a picture of what ours looks like because it's a little easier to explain that way. So the AFMBR is basically a PVC pipe chamber, and then there's a series of membranes that are within that chamber, and they're micropore membranes. They look kind of like coffee straws, but a different material and a little more malleable. So, so the water is pumped into the AFMBR and through those membranes, and the clean water comes out of the pores of the membrane and is pumped out, and the water that doesn't make it through the pores gets pumped back in and circulated again until it's of a quality that can be pumped out. So in AFMBRs we see, we're supposed to see good COD removal, which is obviously a big deal when you're treating wastewater. And so as you can see here, so this is the pump that's pumping in and pumping around, and then this is the recirculation pump. So so we would have like our influent, which would be considered wastewater treatment plant effluent, which gets kind of confusing sometimes. And that gets pumped in, and then the good water comes out, and we'll pump that into like another beaker, and then whatever is left over that still needs further treatment is recirculated with this bad boy. So what we did this summer was build that, which took a little bit of time because I don't know if we're not a very big, or I'll put it this way, we're not Penn State, so we don't have these items just lying around. So like one of the problems we had was we needed a top cut off a Hungate tube, which involves cutting glass, and that was like, it doesn't sound like that's a big obstacle because it like isn't really at a large institution because they have people that do that kind of thing, but here it took us like a good 2 days to like sever off a top of a tube to put on the top. So and when we went to Penn State to ask them where they got it, they just said, they were just like, I don't know, it's just in a drawer that we found. So so there are some obstacles like that. But yeah, so that kind of was a hindrance when we were making it, because we know what the layout is, we know what it's supposed to look like, but you have to accumulate all those pieces and order it. And this wasn't necessarily something we were doing before. So I had a great time. It's a great learning experience if you're interested in going to grad school or not even. But I think it's like really important to do research, and I would suggest that everybody like at some point here does some type of research. It's fun, you'll learn more, you feel better in the lab. That's all I really have to say. Shameless plug, if that sounded interesting to anybody, which I'm sure it sounded interesting to everybody, then please talk to Dr. Wagner or I, because I'm graduating. So if somebody would like to continue this research for the rest of their time here, that would be sick. If you don't know where the lab is, it's top secret. It's actually it's in that parallel hallway in a room that looks like a storage room, but it's actually the St. Francis Anaerobic Fluidized Membrane Bioreactor Lab. So don't be fooled. And I can show it to you sometime if you're interested. But yeah, shameless plug. Do research. Have a good time. Hopefully that was mostly right.
You should just be able to hit enter.
Okay.
One slideshow.
Okay, I'm Jess. Over this summer and the summer before that, I worked at RK&K. It's an engineering firm in York. These are kind of the areas they specialize in. The only interesting one to us is environmental. So the one at my firm is actually the only one that has specifically ecological engineering, which is stream restoration. So overall they have 21 locations in 8 different states. So they're kind of all over the place on the eastern side of the country. There's 4 in Pennsylvania, there's Harrisburg, York, Allentown, and somewhere else. I forget the last one. So King of Prussia, yeah. So my favorite part of my internship was doing field work. So when we do field work, we take a profile of the stream. So we run a 300-foot tape we have to go from the start of a riffle, through a pool, through another riffle, through a pool, and then to the top of the next riffle. So we're trying to get the big drops and change in the actual stream bed and the changes in water level. And then we run another tape across from bank to bank so that we can get the profile of the bank, and that helps us predict erosion. So we use this thing called a laser level, which is the thing on the left. So you get this huge, kind of like a meter stick to measure, and you stick a laser detector on the top of it, and then you just move it up and down until it hits an even beep, which tells you the elevation. And then we go back to the office, and we can enter all of our data into Excel, which gives us it actually plots it out for us so that we can see what the bank looks like. And then once that's finished, we take BHI and NBS, which are both used to help us predict the erosion rates. So When I first started, I kind of wondered, why are people spending millions of dollars doing these kind of projects? Like, what are they getting out of it? So whenever you're building a new road or a building or anything, and you're going to impact a stream or a wetland, you then have to make up for it in what they call points, so they can get their points back by restoring something like another stream. And then after we predict the erosion rates, we can use streametrics, which is like a bunch of contours, and you can click on one point and it delineates the watershed for you. So if it's raining, like, all the water in that area is going to come to your stream, so you can predict how much water is going through your area of interest. And then we put that into GIS, and sometimes it's not quite accurate, so we have to go through and kind of fix little things about it. And then we try to find the longest path so that we can find how long it takes a raindrop to get from one point on the furthest point on the watershed area to the end point. And then we use Flowmaster and HY8, which are both similar programs. They both are used to determine how big of a pipe you might need or how big of a culvert. So anyone in AutoCAD, we just did the project or the assignment where we had to size the pipes. It's very similar to that. And then the last thing they do is they design it on MicroStation. So I haven't had a lot of work with the actual design process, but basically there's like these different programs within MicroStation that can kind of tell you where there's a lot of shear stress, so where you're going to have a lot of erosion. And they're redesigning it so that they want really, really small banks, like a foot high banks, so that anytime it rains, all the water flows out over the floodplain, which helps stabilize the actual bank and helps keep a lot of like plants living there, because that also helps to keep the banks stable. So some fun facts. Does anyone know what kind of plant that is? It's an invasive species. David? Eric? Ashley? No. Sawyer, do you agree with us? Yeah, kudzu. So this can grow up to a foot per day, which is super fast. So we had this one site we went to, and before you can actually start building something, you have to know where all the things that were built previously were. So we had to walk around here, and there were, like, we knew from as-builts, which are records that you find online that tell you like where storm drains were or where like water lines and sewers are. So they were like, okay, there's supposed to be 2 or 3 storm drains in this area. So we had to walk around and find them in this huge valley of kudzu. So my company was voted #1 in Baltimore place to work for based on workers' surveys. So it's a good company. I don't actually work at the one in Baltimore, but it kind of carries over to all their offices. It's very laid-back atmosphere, and everyone's really nice, so I like that. I guess, I don't want to say highlight, but the most memorable thing of the summer, we were doing a field day around Baltimore, and we smelled this awful smell, and we kind of figured it was a deer or something. And then like a month later, this detective came and asked my coworker if anything suspicious had happened, and he took him to the area we smelled it, and they found a body. So yeah, so that was kind of gross. So when we design our new floodplains for the stream, we have to design it for the 100-year storm, which is just like the probability of a storm big enough that happens every 100 years. So that something like this doesn't happen. So the picture on the left is pictures downstream or upstream of this picture on the right, and the one on the right is what it's supposed to look like. So that's how they designed it, and then I guess over time, plants grow up through the cracks. Plants grow up, and they can end up cracking the concrete, and then once there's a huge storm, it moves these huge, like 10-foot slabs of concrete downstream. So if you didn't know how powerful water can be, that kind of shows you. That's it.
Oh boy, here we go. All right, for those of you who don't know me, I'm Josh English, and I had my internship at a company called Biomost, and they're a pretty small environmental consulting firm, and they're located in Mars, PA, which is, I don't know, 20 minutes from Pittsburgh. And there's actually like a collaboration of 3 individual businesses ran at Biomost. It's Biomost, which they use for profit, Stream Restoration Incorporated, which is a nonprofit, and Clean Creek Product, which is also a nonprofit. Like I said, they're pretty small, and they have 9 full-time employees and 10 over summer, including me. So how I got this internship? Well, I let my professors know, and I was just like applying everywhere, and I told Kelsey I was looking for one, and she reached out to me about Biomost, and because that's where she had her internship, and she was still in contact with them. So she set me up some contact information, helped me edit and finalize my resume, and then she set me up an interview with the PE at Biomost, and his name is Buck Neely. And it worked out pretty well because instead of me driving to Mars to get the interview, he actually came in for a seminar one Friday, and before he presented, he just interviewed me real quick. And it was a pretty non-typical interview, pretty informal. I pretty much wore what you're looking at, just like normal everyday clothes. And we just discussed my resume, like my future plans, like my interests. I think one thing that's overlooked when you're interviewing is like your interests. I think it's super important because employers aren't just looking for like someone who's really smart. They want to look for someone who they know they can work with and collaborate with, you know. So at Biomost, I did a pretty wide range of tasks. I really didn't do like stuff that environmental engineers would do per se, but I carried out the plans that they made. So I collected and documented water samples frequently. I learned to run heavy equipment, which is pretty interesting. It was fun. With this equipment, we dug vertical flow ponds, settlement ponds, diversion ditches, and limestone channels. And once we finished these projects, we always had to go back and re-veg, so, you know, throw on seed, hay, whatever. And one of the coolest things I got to do when I was there was help to install a micro hydro generator. And it's pretty sweet. I have a picture later, I'll explain more there. But then I also mapped out wetlands using GPS technology. That was pretty tough. It was like 6 acres of wetland, and I documented where like rock piles were, where fallen trees were, where there's little islands, where there's stags. It was completely out in the sun. It was like 100 degrees both days I was there. It was a tough 2 days. It was very hot. And then, okay, that was not the worst thing. I lied. The worst thing I did here was sifting iron. It was horrible. I mean, it's okay in small doses, but doing it like weeks straight, you're just outside in like full clothing, sifting huge amounts of iron and just throwing dust everywhere. You're literally stained orange. I was stained orange the entire summer until I left and came back here. I'll show you a picture of that here too shortly. But also, since I was an intern, obviously I did kind of the stuff no one else wanted to do, you know, like clean up around the shop, weed whack, mowed grass every once in a while. So my time here, the biggest things I learned was that things not always go as planned. Like you might have a plan laid out how you're gonna accomplish something, but things happen, like things break. So you have to be willing to improvise, and you must always be prepared for setbacks. And like adding on to that, just because it looks good on paper does not mean it'll work in the field. Whenever in the future, whenever you guys are, me too, like making plans or hopefully drafting something on AutoCAD or something, just because it like looks good on paper, you got to think about who you're hiring for the consulting of this job, like who's going to actually carry out the field work. You need to ask yourself if this is even possible with the equipment they have. Because there's a few times where we were doing stuff and, well, I'll just explain a scenario. We made this diversion ditch, and they wanted a 1-to-1 slope, and after we dug it, we had to drive down into it and dump in some media. And a one-to-one slope, I don't know if you guys know, it's basically just, like say it's 1 foot, 1 foot. So something like that steep, roughly. Probably, it's close. But anyway, I started to go down it in the skid loader with a bucket full of media, and instantly just like straight over. I didn't flip it. It was scary, just put it that way. But I got back up and I was like, no, that's not gonna work. Like, I'm gonna hurt myself. He's like, yeah, you're right. I'm like, I'm not gonna do that. So we changed it to 2-to-1 slope, and it worked out pretty well, and they didn't really care. So, and then obviously, since I was carrying out the plans, I learned how to like read engineering plans and blueprints and how to actually carry them out in the field. So I have a pretty vast amount of pictures for you guys here. I'll try to go through them really quick. So here's me and skid loader. This is day 2. Got stuck pretty bad. So that was good. It was pretty bad. It was fun getting out. There's the equipment I ran here and there. Mostly the skid loader. I was in skid loader probably 35 hours a week. a lot of skid loader. Another thing is when you're at consulting firms, every week's just not 40 hours. Like some weeks it's like, 25, there's not much to do. Other weeks I worked 70 hours one week. It kind of all depends. Like if you have a job that needs to get done, then you have to put in the time to get it done. Like that's the big thing about engineering. You gotta meet your deadlines. Here's me. Well, here's the iron I had to sift. First had to be dried. So that's just drying in the greenhouse. I actually built this greenhouse. I'm kind of proud of it. Yeah, the first day I was there, they said, "Hey, go build a greenhouse." I'm like, "Okay." And that was all the plan, like all the directions they gave me. So I just kind of went for it. Here's a picture of a aeration device they use in a vertical flow pond. All the air coming out of this is powered from a trompe, and this trompe is huge. It's 12-inch diameter pipe, and it goes like 20-some feet into the ground. I have a picture of it up here coming up. There's like a zoomed out picture of the flow pond, the inflow pipe, and here's the top of the trompe here. We actually disproved this theory of the trompe. These little pipes right here, it's used like first off it drags air down, but it also restricts it also changes it changes the diameter of the pipe, makes it smaller, and that causes it to pull down the air, pressure difference, and you learn about it in fluids. Trompe. The microhydro generator. So water comes in, it spins this little water turbine, and it charges these batteries that are set in here. And these batteries they power a small schoolhouse nearby for just educational purposes, and a few outlets that hikers can use to charge their phone if they're out hiking. But it's all clean energy. Here's a 17-year cicada, which I thought was pretty cool. These are just pipes that have valves in them. An outflow pipe that we had to dig. That's, I don't know, I forget, that was like 150 yards maybe, I'm not even sure. This device here controls the depth of water in vertical flow ponds, so you basically add or remove these plates to determine the water level. That's an aeration terrace, just aerates the water. It's basically like a waterfall, just really agitates the water when it flows down through it. There's a vertical flow pond we built, limestone channel we built. The limestone channel runs into a wetland here, more to the limestone channel, more vertical flow pond, and diversion ditch, which is to the far right there. Mine, there's a picture of mine. We actually had to fill in a mine, and that's me and the skid loader, packing it, filling it in. It's kind of scary, but we got it done. Sifting iron, not fun. Everything's orange, like nightmare. And by the way, I lived in a trailer, a little camper all summer. It was free living. I couldn't pass it up. So yeah, it was pretty cool though. I just had air conditioning and whatnot. So, and then I'll get questions after CJ's presentation.
everyone. I'm CJ, and I worked in a wastewater treatment plant this summer. I know, gross. Say it now. So I worked at the Mattabassa District Wastewater Treatment Plant, which is located in Cromwell, Connecticut. It serves the 4 cities of Cromwell, Middletown, Berlin, and New Britain, Connecticut. It has an average daily flow between 15 and 20 million gallons per day, but the plant's overall capacity is 80 million gallons per day, although it's kind of unnecessary because it's never had over 25, and it's not predicted to have over 60 in the next 30 years, so it's a little bigger. The unique thing about this internship was in 2012, the state of Connecticut approved a 3-year, $110 million plant upgrade, which is one of the biggest the state has had in the last 20 years, and more than doubled the size of the plant. It also implemented new technologies that have not been used anywhere else in New England, and it also added a new incinerator that has never been used anywhere before and actually is being used as like a research tool on top of actually cleaning sludge. So the 3 types of pollution I got to work with: liquid pollution, obviously wastewater is water, so that's water pollution control. Solids, there's obviously solids in wastewater, so that's the sludge and grease. And the other thing that was cool is I got to do a lot of stuff with air pollution because treatment plants produce a lot of gas and have a lot of odor that you have to treat. So that was somewhat unique. So here's the plant. You can see it's fairly large. There's everything from bar screen conveyors to pre-treatment to primary treatment to aeration to clarification, 4 disinfecting points. Over here, this is they actually have 3 different incinerators. One's the main one, then there's a backup, and there's a backup to the backup, just in case. Again, a little unnecessary, but they had it. Ash lagoons. So it's pretty big. The whole summer I was there, it was never running more than 50% capacity, so I never got to see it fully running, but I was still got to see a lot of it work. So most of my summer I spent doing maintenance work. The bulk of that was the typical internship type stuff: weed whacking, painting the hallways, cleaning the bathroom, planting grass, hedge trimming. So a lot of the boring stuff that anyone who gets an internship is going to have to do at some point. A lot of off-site maintenance. Spent a lot of time off the plant. The sewage treatment plant actually owns the pipe, so all the land that the pipe runs under, the plant actually owns. So if you build a building on top of the pipe, too bad, the plant still owns all that land. You have no choice, even if you build your building there. Like, it goes through the parking lot of a Walmart. Walmart doesn't own their parking lot because the sewage pipe goes underneath it. So kind of unique. And they also own their own landfill where they put all of the ash that comes out of the incinerator. And then, of course, fixing stuff. Stuff breaks every day. Like, stuff just blows up or just stops working or spills stuff or leaks or whatever. But I got to see a lot of people come up with unique solutions, because if something blows up, you can't just be like, oh, just put a new one in, because they usually don't have one. So a lot of the people I worked with were mechanics by trade, auto mechanics, industrial mechanics, people who worked in the Army as mechanics. So they had a lot of different experience, and it was really cool to sit in meetings with them and watch them collaborate and engineer some solutions that were, not so typical for those types of problems. I also had to do a lot of stuff in the lab. A lot of the stuff we did I had already done here in either Measurements 1, Measurements 2, or Chem class, or am learning about now. Stuff like total suspended solids, which is a procedure that's outlined in standard methods for all the tanks. Dry weight of outside sludge. The plant is also the only plant in the country to accept an equal amount of outside sludge as inside sludge. So they charge people to take in all of their sludge. So smaller wastewater treatment plants that can't afford an incinerator or a landfill or whatever, they can pay to ship it here and they'll take care of it for them. This picture is a settleometer test, which is basically in the morning, an operator goes, fills up a 5-liter jug of wastewater, and they dump it in this thing and they let it sit there and they just wait. And then once it all settles to the bottom, they write the number down and the amount of time that it took. Pretty simple test. pH, turbidity, basically like that. BOD, lots of BOD tests. They probably run, the rack of BOD tests was probably 100 to 200 BOD bottles, because they have to do a lot, because that's like the only thing the EPA cares about is like BOD, BOD, BOD. So if you learn anything here about wastewater, know how to do a BOD test in Measurements 2. Fecal coliform and enterococcus using a quantipack method, which is a really cool method where you basically dump the sewage into these little packs and you put it in a machine and then it tells you, oh, there's this many of each of these in this sample. It's pretty cool. And then the other thing, which I didn't take micro, so it was kind of difficult for me, but I got to learn how to do it, was microbial analysis, where basically you put some of the sludge on a slide and you look at it under a microscope and you see what's swimming around. And you just literally put a tack mark next to each type of microbe you see. And then based on the number you get, you can tell how good or bad the sludge is. And then operations, which is if you're going to be an engineer, what most people who are environmentally related do. I do a lot of paperwork and permitting because that's what all engineers do in their first jobs anyways. So CT, Department of Environmental, or Energy and Environmental Protection permits, budget reports. There's a lot of money going in and out of wastewater treatment plants. So the Excel spreadsheets for those are pretty big, so I got to play with those a little and organize them. And EPA emissions report, I filled out a ton of those because this incinerator was so new, the EPA had no clue how to regulate it, so they just decided they're going to call it a car and say, we're just going to call this a car, and every time your emissions exceeds a car's emissions, you have to fill out a report. So that was pretty much every day, so it was kind of annoying, but that's... Then there's typical plant monitoring. My favorite job was blanket levels, where you take this big tube called a sludge judge and you just jam it into the bottom of the tank and you pull it up and there's a measurement of how much sludge is sitting on the bottom. But you basically walk around each tank and just jam it in the bottom of each one. It's pretty easy. You have to do some chlorine measurements using like a Hawk field kit. It's one of the Hawk kits. Take it out, put the sample in, and tells you how much chlorine is in the sample. Instant effluent data. All around the plant, there's these little Hawk devices that read instantly the things that are going through it. So basically there'll be a main pipe and a little pipe will come in, go through this machine, and it'll instantly read whatever data is on that. So things like nitrates, DO, the pH, all things like that can be read instantly just by looking at a screen. The most boring job, which thankfully I didn't have to do, is the incineration monitoring. There is a guy who is paid to sit and look at a computer all day and see what the temperature of the incinerator is. Sits there and watches it. So that's his job. So how I found this place, basically drove past it every day in high school, so I knew it was there. Applied online, they called me, called my references, offered me a job. Learned some interesting things. One, don't weed whack poison ivy, otherwise you will be covered in it for like 3 weeks. Bad, terrible. Welding is very hard. Do not ask me to weld anything, it'll be terrible, so I can't do that. Tractor tires are filled with beet juice, if you didn't know that. It's a fun fact. Because it's denser than water, but it freezes at a lower temperature than water. But wastewater treatment is actually kind of cool, right? And you're probably thinking like gross, but it's actually a pretty interesting thing. There's a lot of science that goes on in it, and you learn some pretty neat stuff. Questions?
Questions for Jay. Oh, CJ's up here. Questions for CJ. We'll go backwards.
Yes, it was.
What was that, George?
It's a not too funny joke.
Come on, a question. Anybody?
So CJ, how important are your references?
Very. Professor Whitey gave me a very good reference, and they told me that all summer about how great my references were and how nice they were to me.
Jay, you got a question for CJ? Josh?
Josh.
What kind of interview did you have? Phone interview, in person?
None. They called Professor Whited and Dr. Bill, and then the same day called me and said, do you want a job? And I was like, sure. So thankfully none, because I don't like interviewing. But so that's one thing I did not get to learn how to do. So no practice. So because it's kind of a win-lose.
All right. Thanks, CJ.
Jess has a question.
Would you work there once you graduate?
I would. If they were to offer me a job, I would take it.
Do you think they will?
Potentially. We'll see. I'm going back in December to work, so we'll see how that goes.
Okay. Good question. Questions for Josh? You want to stand up, Josh? Questions for Josh? Back corner. Over there. Anybody? Will.
Did you guys have any kind of training to run those machines and stuff?
No.
Kind of like your runners?
I don't think so, at least. I didn't. It's probably depending where you're working at. Like, since we're out in the middle of the woods, like big ponds, it's sort of not like technical. It's not like we'll be like running into people's cars or something, you know. It's like just me and another guy out there. So it probably really depends on where you're at.
Does Biomost only remediate acid mine drainage sites, or do they do other remediation?
That's the majority of it. But they're pretty much open to anything.
Why were you sifting iron?
They would sift it according to particle size. They sifted it, like one particle size was minus 200, that's the finer stuff. And then another particle size was 80 by 200, which is the middle stuff. And then plus 200, they kind of just threw away. But the two grades, like the finer the iron, the better it sells, I guess. And they sold it off to different people for various reasons. I don't really know why I would buy it, but probably just for like, you know, like maybe for like a university to study or whatever.
Okay. So we bought iron from them before that they've sifted to use in experiments. And they also sell the clay increase products you mentioned.
Yeah.
They sell it to potters and they add it for pigment.
Yeah,
And
they
then
make
also
paint.
then for paint and for brick pigment. Anybody else? No? All right. Time for Jess.
Will you help me with my senior project?
Yes, we should help out.
Anybody else? Over there? Anybody?
Yeah,
Sawyer?
You mentioned about an online kind of like database that had like information about where pipes go underground or something like that. What was it called?
I don't know the actual database. They're called as-built.
As-built.
So
Okay.
based on the county that you're in, that you're interested in, you can look into that county, and it's really hard to find them actually because they're all like originally they had to hand draw everything before AutoCAD and MicroStation. So you have to kind of look based on street names
Okay.
and try to find them through that.
Okay.
Yeah.
Did you hear about the dead body in the news?
No, I did not. I tried to look up an article and it wasn't anything.
Another good question for Jess.
Yeah.
What city was it?
I worked in York,
Okay.
but they have a lot of different locations.
Questions for Hannah? There?
Do you make electricity with those AFMBRs in addition to like treating the water?
No. Actually, the purpose of the AFMBR is that it's low energy, so it's like a more sustainable way to polish wastewater, and that's like where the practical purpose for it is that it's low energy. So because the water is being pumped in at a really slow rate, so it doesn't take a lot of energy to pump it through, and so then it's just like more, obviously like more cost efficient and that kind of thing. And then I forgot to mention this before, but there's like surrounding the membranes, there's granulated activated carbon, and there's, which is obviously like, it has like lots of nooks and crannies. So microbes will, because you're pumping in still like wastewater treatment and effluent, there's still microbes present, and so those microbes will like latch on to the GAC, and that forms a biofilm, which also helps to treat it, which makes it like even more like, sustainable, because it's just like microbes doing the job. Great question. Josh?
If someone was going to pick up your research, would you recommend them just pick up where you left off, or kind of, start where you started and work their way up?
I would recommend that they, focus on the AFMBR, but it's still good to understand the principles of FOCs. But I would recommend like reading scholarly articles about AFMBRs because it's not necessarily like an easy topic to just like pick up and understand. So I would suggest like a good portion of background research, which is kind of like where we started to, not this past summer, but summer before, where we just like took a couple weeks and just read about it. Because there's a lot of different ways, like different spins you can put in it for different reasons. So I don't think that it would be an easy research project to just kind of like jump into necessarily, like right away, because we won't be able to do a lot. But by all means jump in, but wait about it, I guess.
Any other questions?
So yes and no.
All right, thank you. Maria. Question for Maria.
It's compliance environmental.
I mean,
Oh, like,
actual.
oh, it was in Hermitage, VA. It's like on the border of Ohio. No one knows what that is.
Questions over here from Maria, this side of the room. Ryan?
Would you work there again?
I'm going back there in December. So yeah.
So the data that, like the lab tests that you generated, how would they use that data then?
The plate counts are used to figure out like how much bacteria that uses the benzene stuff was in there, and then they would, if they was already remediated, then it would like, okay, like there's none there, so I have to remediate all of it, or like if there was like a certain amount of it, we would like add more culture or scale it up.
All right. Any other questions for Maria? You gotta hurry up. There's another class coming in. Questions for Jay?
Josh.
What was your least favorite and favorite thing you did there, and would you go back?
No, I won't go back. my least favorite thing to do would be like the companies would send in like 7 bags of samples, but we would only use like 5 of them. So like for every like sample we got, there's 2 like 60 to 90 pound bags of rocks sitting out in the hallway, and so like once a month we'd have to like take it out to this dumpster and like empty it out and like shake it. So like you're like have like this mask on, and like it's like July and August, so you're like baking inside this dumpster, just like shaking up these bags. And then my favorite thing would just be like the overall environment of it. Like the guys were pretty chill about everything. Like they didn't work. It was just really relaxing. We played basketball every day during lunch, so it was just cool just to like just like not feel pressured to like fail or like to succeed. They're just like if you screw something up, they're just like, it's alright, it's just rocks, like. No.